Hello, in this section we were talking about how we costing the anodes. My name is Yongtao. I work currently in Energy Market and Technology Department in DNVGL Energy in Oslo, Norway. In promotion project, I'm working in a few work packages, among others the work package 2 and 4, supporting the HVDC grid modeling and the protection system designs. In work package 12, I'm act as a task lead for the cost data collection for offshore power transmission system. In work package 16, I'm working on the control hardware and power hardware in the loop testing of wind turbine generator and MMC VSC converters. This presentation is mainly about the work we are doing for work package 12, the cost data collection. This is done with both with colleagues in DNVGL, but also with a few other partners. I'd like to start with an overview of the components for where we would need to collect the cost data. To be able to collect the wind from offshore to onshore, we are using different connection approach. Here we show a point-to-point connection, both for offshore wind, but also for the interconnector from the between the countries. And then, of course, we can, in the future, we'll also envisaging a more coordinated build-out where you connect them via a grid, offshore HVDC grid, as shown here. Of course, this within this, you can see that you can recognize that we need the various components for this tool structure, among others, the converter stations, the AC transformers, and also cables. Especially for the coordinate or grid structure, you need a different fault clearing device for the HVDC grid. Let's say the DC circuit breakers. And also for a grid, you also need a grid control center. And for some of the design, you will need a power hub or artificial island. To be able to build the HVDC grid as shown in previous slides, we need both existing technology and emerging technology. And we also know their cost in current at the moment, but also in the future. Here, for the existing current cost level of existing technology, will be mainly based on the or public available information, literature review, and some of the in-house data, which we will not go into detail in this presentation. The next quadrant will be the current cost level of emerging technology, which will be the first part of our presentation. On top of that, we will also need the future cost, which we'll talk about in the later half of the presentation. So how do we estimate the current cost level of emerging technology? There are two models. One is called Inferential Model, the other called BottomUp Model. We'll show them in the following slides. The Inferential Model. This is the model we use to estimate the cost of a emerging technology based on a similar component which it has been quite mature and you have available cost information. In this here in this slide, we show the example for a 4-bridge MMC VSC converter, which is still a new product, which has rather limited available information on its cost from the existing projects. So what we do that we use the cost of half-bridge VSC converter with identical power rating and voltage level as a base. In here we can show that to the left is a sub-module of a half-bridge VSC converter. To the right is the full-bridge VSC converter. Basically, we start with investigate what is the difference between these two in terms of number of power electronic devices, dimension of converter transformer numbers, and dimensions of passive components such as capacitors. Then based on the comparison, we establish the cost difference between half-bridge VSC and full-bridge VSC based on the material cost difference. To this example, we show some of the high-level calculations. Bottom-up model. This is the model we use to estimate the cost of emerging technology, which is so unique that you do not find a similar product, existing product that you can base on. For instance, the HVDC circuit breakers. The first step we do is reconstruct the principal structure of the component. Such as the hybrid DC circuit breaker structure as shown here. Then we will establish the basic configuration of the different component and their dimensions. Based on that, we will estimate the material cost, or the material cost included in this configuration. Further on, we will add additional cost such as research and development, business margin, installation, etc., to obtain the overall the total cost of such a component. So that's the method we used for, especially mainly for the DC circuit breakers. As mentioned before, we will need not only the current cost level, but also the future cost level towards 2050. A HVDC grid consists of several various components such as VSC converter stations and DCCBs and cables and offshore platforms. For each category of the components, the cost is split into several cost elements, such as shown here: equipment, installation and transportation, civil work, PM, right-of-way, profit margin, and risk contingency. For each of those cost component is further determined by a few cost drivers. For instance, the cost of equipment is further determined by labor costs, which we referred as the cost, the working hours of lower scale labors, and then energy, engineering hours. This is a highly skilled workers hours, and then commodity and metals. For each of those cost drivers, it could further determined by at least two factors. One is the unit cost of such cost driver, and then the quantity you need for such a cost driver. In this example we assume that the labor cost, unit cost of labor, will be kept constant towards 2050, but we see a significant decrease of the quantity needed for the labor in this specific component, which is actually the onshore and offshore VSC converter stations. In this analysis, we make this following assumption on the major trend. First is automation. We see that the artificial intelligence, robotics, and other forms of automation will most likely advance at a rather rapid pace and will boost productivity. In this analysis, we will assume that the amount of labor and engineering hours needed in production, installation, and civil work and PM will go down in the coming decades. Then the cost of commodities, this is like aluminum, copper, steel, power electronics, XLP, and raw oil as fossil fuel. Will use mainly the World Bank prognosis. The cost of energy, as we should know that the production of equipment, installation, and transportation, as well as the civil work, will require energy. We'll focus on the change of energy mix from fossil fuel to electricities. And then also we consider the impact of energy efficiency. For the same amount of work, the energy needed will be likely going down in coming decades. In this slide, we illustrate an example how we do the cost development forecast of an offshore VSC converter station. To the left, you could see recognize the different cost element, and then you see they are consisting of different cost indexed cost drivers, and then how they are changing over the years towards 2050. And by summing them up, you get a overall cost development of such a component towards 2050. In these slides, we illustrate a summary of the results for price development of HVDC equipment towards 2050. Here you can see that these two curves show the subsea cable and underground cable. They have a less steep cost reduction towards 2050 in the level between 10 to 17%. Wow, the other four categories like offshore platform, offshore converter station, onshore converter station, and the DCCB, they all have a much deeper cost reduction potential, between 30 to even to 40%. That is because we believe that there's a huge amount of potential to be cost reduction potential due to the higher amount of R&D cost today, and which will be likely going down substantially in the future. So we also make a comparison of our cost, our model, and the so-called learning curve, which is based on the volume. It also has a name of Wrights Law. Basically, it says that with a cumulative doubling of production of certain component, the unit costs will be decreasing by a certain percentage. This here we show the cumulative installed capacity of VSC towards 2050 based on our prediction on based on the historic data, and also the correlation between the increase of VSC converters and the GDP, and also combined with our prediction of GDP growth in 2050. Here, of course, you can see that we predict the cumulative installed capacity will be increased from around 30 gigawatt in 2020 to around 270 gigawatt in 2050. Using such a prediction, we compare our cost level, which is the blue curve, with two different reduction. It's the light blue is the cost reduction. Assume that for each double of installed cumulative installed capacity, the unit cost decreased by 10%, and the green curve is the same, but with the reduction by 15% reduction. So you see that our prediction is somehow in between those two curves. A summary of this presentation for costing emerging technology in the current level. We have two methods, inferential methods and the bottom-up methods. For assess the cost development in the future, we propose a framework, basically breaking the cost of overall components into cost elements and further into the cost driver, and then assess the impact of the major trends on the cost drivers. And the results shows that they agree well with the learning curve effect of 10 to 15% cost reduction per doubling of accumulated capacity. You're welcome to raise your question in the QA session, but also you are also welcome to contact me afterwards. Thank you.